We are discussing the simulation, and in this particular topic we have already discussed the discrete event simulation system in detail, and additionally we have also discussed Monte Carlo simulation. We have also discussed an discrete event simulation language by the name Arena, and we are now into our last topic in the simulation, that is continuous simulation and system dynamics. See, unlike the discrete event simulation, the continuous simulation is different. In continuous simulation, as you see that we have first of all both deterministic or stochastic variables are there. You know what is stochastic is that probabilities are involved, and these probabilities themselves are dynamic in nature. The second thing about this model, that there is events are not occurring, however, the state or the system state through which the continuous system that we are talking about is represented, those variable values are changing with time. So, it is dynamic, and finally, they are actually continuous in a state, because the state changes continuously, as it is already known, because it is dynamic, and these state changes are guided by a set of differential equations. Now, not in all cases the equations may be differential. We have those econometric model where we really do not use differential equation, but we use a variant of that. So, more or less conceptually things are similar, only thing the form of the equations are slightly different. Now, here are some specific thing, that in continuous simulation model there are no events, changes expressed in terms of differential equation, and system state evolves continuously in time. Because there are no events, random numbers are not required, right. So, that is one major thing, that we are really not talking about distributions, random numbers, random variates, these things are not required. Examples, the examples could be, first of all there are classical mechanics, then there are econometric, and then finally the system dynamics, which is a full fledged theory in itself. How can we model what is known as societal systems or socio-economic systems, or even sometimes physical systems. These are the three broad examples that we shall see in our subsequent course. First of all, let us look at an example of the classical mechanics. You know, in classical mechanics, what happens? First of all, when a particle moves, the particle is moving because it has a velocity, right, and because it has a velocity v, it is having a displacement. Additionally, it can have an acceleration, and because of this acceleration the velocity also changes. So, these are the equations. What are the equations? Look at those equations. First of all, the acceleration dv dt equal to at, a is for acceleration, and velocity also itself is a differential equation, that is dst dt is vt, and displacement we know st. Now, instead of keeping those equations in the differential form, they can be also expressed in the difference equation form. How? Let us see that. Supposing we have, let us say, ds dt dst dt equal to vt, because you know that is the velocity equation. We know d dt of st is basically nothing but limit of delta t tends to 0 s t plus delta t minus s t divided by delta t, so equal to v t. So, we know that you know this d dt of s t is nothing but limit of delta t tends to 0 S, that is displacement, t plus delta t minus S t by delta t equal to V t. So, this will give us that S t plus delta t minus S t equal to delta t V t, where delta t tends to 0. Now, assuming delta t equal to dt finite, then we have really S t plus dt or this dt equal to minus S t equal to dt times V t plus higher order terms. Or in other words, S t plus dt equal to S t plus dt times V t neglecting higher order terms, right. Basically, you can even delete this equation, because from here itself, if you straightway write delta t equal to dt, then you can get this form, right. So, this form may or may not be possible to write. So, once you have this, then you can get this particular form, and this form is called the difference equation form, right. Obviously, here you must have dt to be sufficiently small, and this is called Euler's form, right. So, this is an Euler's form. So, look at this slide now. So, basically same thing has been written, used Euler's form, and you can write the difference equations in this form. So, can we generate velocity and displacement profiles from these equations by simulation? So, how can you generate the velocity and displacement profile? So, given acceleration profile, so we have to have something, we have acceleration profile. What does it mean? It means that if this is time and this is acceleration, then this plot is given, right. So, if this is t, this is t plus dt, this is t plus 2 dt, etc. So, this graph is known. So, if this graph is known, supposing we know at, we know Vt, we know St. A special case, we know A0, we know V0, we know S0. Like that, 0, I mean assume t equal to 0 initially t equal to 0, and at plus dt is known. All these at values are known. So, we know Vt is an integration. So, Vt plus dt equal to Vt plus dt times at. So, we can know Vt plus dt. Similarly, since St plus dt equal to St plus dt times Vt, we can know S t plus dt. All right. So now if we replace t plus dt by t and repeat, then what will happen? You can know V t plus 2 dt S t plus 2 dt. Why? Because A t plus dt is known, right. So, like this we can know all of these values. So, we know Vt, we know Vt plus dt, we know Vt plus 2 dt. So, we can generate the velocity and displacement profiles, right. So, we can generate these profiles. So, that is the real thing about these classical mechanics, that we can generate velocity and displacement profiles. So, same thing is written here, that if we know at, Vt, St values for t equal to 0 and for small dt and neglecting higher order terms, we can find out the subsequent values and generate the profiles, right. So, this is how we can actually continue simulation by solving. Essentially, what are we doing? We are solving those differential equations numerically. One point must be remembered, while we do like this, there could be some errors due to the neglecting higher order terms. How to reduce this error is a very important thing, but one must we may remember that if we take sufficiently small dt, these errors will be small and it may not affect that much in our simulation. Is all right. Or what we can do, we can use better equations than difference equations. Those are available in the numerical analysis theory, right. Now, we take up the other one, that is an econometric model, which we can call the distributed lag models. So, these models are continuous simulation models and the properties change only at fixed interval of time. So, current values of the variables are based on current values of the other relevant variables or on values of the variables that have occurred in the previous intervals. So, used in econometric studies where uniform steps are related to time intervals over which data is collected and consist of linear algebraic equations. So, here is an example. So, suppose we have a model of national economy where C is consumption, I is investment, T is taxes, G is government expenditure and N is national income, right. So, we have certain equations and these equations are C equal to 30 plus 0.8 star n minus 1 minus t minus 1, right. N minus 1 and t minus 1, they are 1 period old values. Similarly, I equal to 3 plus 0.2 n minus 1, n equal to c minus 1 plus e minus 1 plus g minus 1 and t is 0.3 n. Obviously, these are all econometric equations, but we can understand easily because tax is assumed to be around 30% of national income, right. National income is last period consumption, investment and government expenditure, that is called national income, and investment is equal to 3 because it is some kind of equation. What was the national income? So, 20% of the national income plus a constant value, that is taken as the investment, and consumption is national income minus taxes. So, that is the money that is available and 80% of that let us say is consumption plus a constant value 30. So, these are some equations. Now, assume that we really want to simulate. So, simulate means we have one set of values. Using that one set of values, can you compute the next set of values? That means we have all the previous values, and using those previous values can we calculate all the next term values. So, here let us see we have all the -1 values, right. We have C -1 values, I -1 values, N -1 values and T national this thing, but we do not have, let us say, the government expenditure. So, what we can do? We can take government expenditure as a kind of independent variable, and suppose we know the government expenditure variable profile, right. So, if we have that, then probably we can calculate all the others. Let us see how. So, you see the same equations are written here. So, you see C last 1 year old values, I 1 year old, T, G, N, all the 1 period old values is known. So, we also should know what is known as the government expenditure profile. So, that means we know all the G values, right, starting from G0, G1, G2, G3, G4, G5. So, using all the 0 values, we can calculate all the 1 values using these equations. Then using all the 1 values, we can calculate all the 2 values. So, like this we can keep on calculating, and we can generate the profile of C, I and T. That means, how they vary over time, all of these variables can actually be obtained. So, that is the essential idea of such distributed lag models, and such models are used in econometrics, right. So, our third one, that is we can look at the system dynamics model. You see the system dynamics model, we can discuss this in detail, and these are some models which were originated by J.W. Forrester in late 1950s and in the Sloan School of Management at MIT. So, system dynamics, originally this was known as industrial dynamics, and that was the name given by J.W. Forrester at MIT, right. So, that was how it originated, but after it has originated, it has passed quite a bit of transformation, and in fact, today one of the best book on system dynamics is known as Business Dynamics, right. So, this Business Dynamics book written by Starman of MIT, right. So, you can look at this particular topic, this book Business Dynamics, to know further on this topic system dynamics. Now, what is system dynamics? You see, first of all, there are several things that are required that it does. First of all, it addresses long term issues of real systems, models complex nonlinear relationships with ease, models feedback processes, able to model soft social and psychological variables, tests effects of alternative policy options and communicate results and recommendations with ease, right. So, it is a methodology of social system analysis and design at the aggregate level using continuous simulation. How it does? Let us look at an example, right. You see, first look at the flow diagram. What is really happening is that supposing a particular material is required, and when you require this particular material, we keep a store or an inventory for it. Then as we order the material is in the transit. Then after some time, after the delay period, the material arrives. As the material arrives, it is taken into the stock and it is consumed. So, as you are consuming, the store reduces, right. So, suppose we are trying to simulate, we have also seen how such models are modeled in discrete event simulation. The difference here, there it was done through a random number, through an event based exercise. Here we shall do the same thing, but with a set of differential equations. So, look at this diagram once more. You see there are two types of variables mainly in the main physical flow line. Is one type of variable which are called rates. So, we have the order rate, we have the incoming rate, and we have the usage rate. The other types of variables which are called accumulations, they are like materials arriving and inventory. So, these are called rate variables and these are called state variables, and they happen in a physical flow, right. A material is flowing. So, here we are ordering the material, here the material is coming, and here the material is in order form, here the material is actually coming after a delay time, and that delay is called a supply delay. So, let us say some delay takes place and the supply delay is taking place, and then the material joins the inventory, and finally after usage the material goes out. Is it all right? But question is that then how much should I order? And let us say a very simple policy is followed by the company, that whatever we are using, same thing we are ordering. Suppose that is what we do. Is all right? That is the model, kind of model we draw in a flow diagram. All right, we shall see that in detail, and here is the same thing shown in another diagram which we are calling a causal loop diagram. So, you see, if you look at the causal loop diagram, then as the material arriving rate, material arriving rate, and that is the nothing but the order rate. The order rate, sorry, the material arriving, this is the material arriving. The material arriving is increases as you order, and as you order, then the material arriving increases the in rate. So, this is this part of the diagram, and then as the material incoming material then it is goes to the inventory, and then through the usage rate and order rate it is actually modeled. So, now all these models, we have a steady state conditions for the model when a change is brought about in A and the resulting change comes in an immediately and adjacent variable B. So, that is the essential meaning of a causality. So, let us see what is causality. Causality is, we say that A causes B, right. So, let us say in a plus manner. What does it mean? You see, A and B are taken from a system. A and B are taken from a system, and in this particular system, what is we have is that as we increase A, the B also increases, but there is a particular requirement that all the other variables remain constant, right. All the other variables remain constant or in equilibrium. Sometimes we may not be able to keep exact equilibrium. So, they will be in equilibrium or near equilibrium. So, and then we make a small change in A, and if there is a corresponding change in B, then we say that A causes B, right. So, that is the essential idea of causality, and if A increases, B increases, then we put plus. If we say A increases, B decreases, then we put minus. So, here are some more examples of the causality. So, A is called the causal variable, B is called the affected variable. So, here is some examples. As you increase production, inventory increases. As you increase depreciation, capacity decreases. As you increase birth rate, population increases. Skill, productivity increases. quality, sales increases, price, demand decreases, more price, less demand. So, like, but there could be a chain also, like more price, less demand, less desired production, less inventory. Because you have to read in, when you read, please be careful that what it means, that when you read demand and desired production, you read only these two, do not see anything else. So, more demand, more desired production. Similarly, more desired production, more inventory. Is it all right? Inventory means stores. So, similarly, look at here, more skill, more productivity. Then look only this, more productivity, more production, more inventory. But when you have a chain, the chain may behave differently. You see, more price, less demand. But if you have less demand, will it be more desired production? No, it will be less, because there is a plus. So, as demand decreases, as desired production will decrease also. Similarly, less desired production, less inventory. So, if you read the entire causal chain, then more price, less inventory. Similarly, between skill and inventory. So, we can have multivariate causality also. So, like there could be order, backlog and inventory, and if you take them together, then sales rate may change. So, both the two variables are affecting sales rate. There could be another example, that potential demand, quality as well as price, they all may change what is known as order received, right. So, production, potential demand, quality, price, they all together will change the orders received, right. So, look at some examples. Here is one example, that with more advertising, more orders, more advertising. So, it goes, and then we have what is known as a feedback loop. So, this feedback loop is positive, because you see more advertising, more orders, more advertising, right. Again more advertising, even more order rate. So, things are increasing, reinforcing. So, this is a positive feedback loop. But on the other side, more orders, more backlog, more delivery delay, and more delivery delay, less orders. Because if you delay your delivery, what will happen? You may get less and less amount of orders, right. So, here is a negative, because why it is negative? Let us look at this way, more advertising, more orders, even more advertising, but more orders, more backlog, more delivery delays, less orders, right. So, this is the kind of thing that happens. Look at another one. So, it is an interactive causal loop, right. So, more orders, more revenue, more budget for advertising, but more budget, more orders, but more orders, more backlog, more delivery delay, more orders. So, less orders. So, this is a negative. So, that is the multivariate causality gives to interacting causal loop, because order rate depends on both. This is a classical model about the population, birth rate and death rate. So, more birth rate, more population, more death rate, less population, right. But the both birth rate and death rate could be a fraction of population, assuming that these are happening. Then birth rate is a fraction of population, death rate is also a fraction of population. In that sense, both birth rate and death rate may be functions of population. So, we can have a positive loop here and a negative loop here. So, that is a population dynamics. Then another example of positive feedback loop, that more sales, more satisfied customers, positive word of mouth and even more sales. So, this is a positive feedback loop. So, overall as you go once around the loop, then things are in a reinforcing manner. So, sales continue to grow, resulting from positive word of mouth from satisfied customers. On the other hand, a negative feedback loop is what is happening. You see, as you place order, the supply line increases, current inventory level goes up, but the desired level and current level, the gap reduces. Why? Because suppose you want 100 in the store, and currently with more orders, more supply, this has gone up to, let us say, 90. So, the gap is only 10, then you order less, right. So, that is where a negative loop. Look, between, if the gap increases, more orders. So, that is why it is plus. But what is the total effect? As the current supply, suppose more orders, more supply, more supply, more inventory, but gap, more inventory, less gap. Now, as the gap reduces, less gap, less orders. So, we started with more orders, more supply, more supply, more inventory, less gap, and less gap, less orders. So, we started with more, ended with less. That is why that negative. That is why this entire loop is called a negative feedback loop. Is it all right? So, such kind of things do happen. There sometimes there could be delays also. For example, when you take a capacity decision, then only after a delay the capacity comes in, right. And we have the current capacity level that goes up, and as you have perceived gap, then you take further capacity decision. So, we have a delay coming here, that the loop is taking place, its effect is seen, but only after a time, right. So, that is what is a feedback loop with delay. Here is another example where we are calling it the fixes that fail. So, what is fixes that fail? Suppose we have a cash problem. As you have a cash problem, you borrow money, but as you borrow money, your monetary crisis reduces, right. So, more cash problem, more borrow money, less monetary crisis, less cash problem, less borrow money. So, that is a negative loop. But after some time, so this is like a fix, right, borrow money to make payments. But what is going to happen? As you borrow money to solve your cash problem, after some time your debt situation will be worsened, right. So, you will have even worse debt situation, right. So, we put it in a plus in that sense, and more is the debt situation, means worse is the debt situation, more monetary crisis you will be in. So, there is a bigger positive loop around. Just look here, borrow money more, after some time your debts go up, monetary crisis go up, cash problem also goes up, right. So, I stop here and we will continue our discussions in our next class also. Thank you very much.